Well, hello. We're starting a new unit right now. And I believe that unit, which is logs and exponentials, starts with assignment 63. And actually, with assignment 63, we're not actually talking about logs and exponentials. We're going to talk about inverses. Woohoo! And I really want to look at two topics today. One is how do you make an inverse? And I kind of want to talk about how do you know if two functions are inverses? But before that, I'd like to talk even earlier about some vocabulary, like one, two, one function. If a function is one-to-one, what does that mean? And how do you know if a function has an inverse? Not all functions have inverses. Okay? All right, so these are the things that I'd like to look at with you in today's video. Yeah, let's start down here. So, all right. So, remember when we were dealing with composition in our functions unit? I'd like to actually go back to that now. And I'd like to look at, with some bell work, I'd like to look at these functions. F equals 3x, plus 6, and g equals 1/3 x minus 2. Okay? And will you please find f of g of x and also g of f of x? Okay? So I want you to take g and plug it into all the x's of f and see what you get. And I want you to take f and plug it into all the x's of g and see what you get. Why don't you pause the video and give that a try? Hey, welcome back. How did it go? Did you take all of this and plug it in there? And that's a 6. So when I distribute, 3 times 1/3 is just going to be 1x. 3 times minus 2 is minus 6. And don't lose that. Ooh, how tidy. We get x. And if I take f of x and plug it into all the x's of g of x, if I take all this stuff and put it right there, I'm going to have 1/3, 3x plus 6 minus 2. And then when I distribute 1/3 times 3, again, that's x. 1/3 times 6, well, that's 6/3, and that reduces to 2. And then we have this minus 2. Oh, look at that. And we get x. Yeah, that's kind of important. This is an indication for me of something really powerful. And that powerful thing is, this is what inverse functions do. These functions are inverses of each other. And because of that, we could say f inverse of x. This is not raised to the -1 power. I know in your brain you're saying, but that's raised to the -1 power. No, it's notation. It means inverse. In the context of this content, that means inverse. Okay? All right, so these functions are inverses of each other. Now, curiously, one of the things that I know is that if I graph these functions, 3x plus 6 and 1/3 x minus 2. So here's my minus 2, here's my plus 6, is that there's some interesting properties here at work. First, these lines reflect across y equals x. I know, it's pretty cool. Next thing I notice is this. This ordered pair is 0, -2. Well, you know what point is on this function? -2, 0. And this point here is 0, 6. And so what point is on the inverse? 6, 0. What is it that we're doing there? We're noticing that this ordered pair is that ordered pair, and that this ordered pair is that ordered pair. And so switching x's and y's is a way for us to determine, hey, there's an inverse there. But I'm getting off track because what I really want to talk about first is, how do I know if a function has an inverse? And I guess I could say 1, 2, 1 functions have inverses. A 1-to-1 function is not only each input goes to only one output, right? That's the definition of functionness. But also, each output goes to only one input. Now, I kind of want to go back for a second and say, you know, in order to check this back in functions, we said must pass the vertical line test. Well, now we're switching the input and output. And so instead of passing the vertical line test, this is saying must pass the horizontal line test. Okay? So, if my function passes both vertical, if my relation passes both vertical line test and horizontal line test, the passing the vertical line test tells me that the relation is a function, and the passing the horizontal line test tells me that that function has an inverse that is also a function. We are not really concerned with relations where the function is, the inverse is not a function. When we talk about inverses, we want that inverse is also a function. Okay? All right, so when I think about things like this, y equals 3x plus 6. Well, does this have an inverse? Sure, I know what the graph of this is. 0, 6, -2, 0. This passes the vertical line test, so I know that this is a function, but it also passes the horizontal line test. So I know that an inverse exists for this, as opposed to x squared plus 1. You know, this is a function, x squared plus 1. Goodness knows we've crafted a bunch this year. -1, 2, 0, 1, 1, 2. Passes the vertical line test. Does it pass the horizontal line test? No, it doesn't. So, I'm reluctant to throw away all parabolas. But I do want to point out that not all functions have inverses, and therefore not all functions are one-to-one. But let us think about this. Let's look at some t-charts. Okay, 1, 2, 3. 4, 4, 4. 4, 4, 4. 1, 2, 3. X, Y. 1, 2, 3, 4, 6. X, Y. 5, 3, 2, 0. -4. 5, -4, 1. Okay. So let's go through these and figure out if we have a function and maybe if we have an inverse. So functionness, remember, we said if we had repetition in the domain, i.e. this number went to this, and this number went to some other thing. Yeah, that's not happening here. So we note this is a function, but does this function have an inverse? Well, let's see. If I graph these points, 1, 4, 2, 4, 3, 4. So I see that this has no problem passing the vertical line test. But does it pass the horizontal line test? And don't say yes. It crosses all of those points. That means it fails the horizontal line test, and therefore this does not have an inverse. I mean, I can make an inverse, but that inverse is not going to be a function, and therefore we really aren't interested in it. Okay? Just because this is invertible doesn't mean we want to do that. Here, on the other hand, where I have the same x value, 4, 1, 4, 2, 4, 3, I fail the vertical line test. So that's not even a function. Okay. Here, each input goes to one output, but each output also only goes to one input. This has an inverse. We've got 1, 4, 2, 5, 3, 6. I'm going to pass the vertical line test, so I know this is a function. I'm also going to pass the horizontal line test, and therefore I know that the inverse of this function exists. Okay? What else? Oh, so I don't want to see repetition in the domain or the range. No repetition in domain or the range. Okay? So then, how about this one? Is it a function? Does it have an inverse? Is this one-to-one? How can we tell? Well, I like that idea. Look, no repetition here. That means this is a function. But I do see repetition here. -4 goes to 5, and -4 goes to 2. Because each output doesn't only go to one input, this is not 1, 2, 1. This does not have an inverse. And some students don't feel comfortable on doing this from a table. Instead, they want to actually graph these points. So we've got 5, -4, and we've got 3, 5, and we've got 2, -4, and we have 0, 1. Now, I don't know, maybe it's something like this, but I don't really care because, look, fails the horizontal line test. No inverse possible here. If I change this function a wee bit, like that, now it is a function, and no repetition here means now I also can have an inverse. Okay, so let's see what we can say. To have an inverse, I would like to pass the horizontal line test, and I would also like no repetition in the inputs or outputs. No repetition in the domain or range. Great. This is a graphical way of understanding whether the function has an inverse or not. This is a method that I can use from a table and look numerically, but I find that while it would be nifty to have an algebraic approach, if I'm looking at some algebra, like y equals absolute x plus 1, and thinking, does this have an inverse? My first thought is actually, does it pass the horizontal line test? I know what this looks like, and now I've just shifted it up 1. Does this pass the horizontal line test? No. So this does not have an inverse. I think I'm not going to have really an algebraic approach to knowing that. I'm going to have either a graphical or a numerical approach to that. Okay. So I know a function is one-to-one. I know a function has an inverse if the function passes the horizontal line test, if there's no repetition in the domain or range. But how do I make an inverse? Well, remember from the Bell work that we had y equals 3x plus 6, and we had y equals 1/3 x minus 2. And it turned out, I said that these were inverses of each other. So how does this turn into that? Well, it turns out that if we switch the inputs and outputs, if we switch the x's and y's and solve for y, something interesting happens. So let's start here with switching the x's and y's. And now solve for y. So subtract 6. We get x minus 6 equals 3y. And now I'm going to divide everywhere by 3. And look what I get. X over 3 minus 2 equals y. And this could be written as 1/3 x minus 2. Hey, that's that. So, how do I make an inverse? I switch the x's and y's. I switch the inputs and outputs. If I had a table that was 1, 2, 3, 5, 6, 7. Okay, so here's my function. No repetition in the domain, so I know this is a function. And now I want to make the inverse. Well, to make the inverse, I switch the inputs and outputs. 5, 6, 7, 1, 2, 3. Okay, there it is. That's all I got to do. Now, what about graphically? If I see these points, 1, 5, 2, 6, 3, 7. Okay, I've got this function. I see that this function passes the horizontal line test, so I know an inverse exists. And what points must be on that inverse? Well, the points that are going to be on that inverse are these. I'm going to have 5, 1. I'm going to have 6, 2. I'm going to have 7, 3. And what we're going to see is a reflection across the line, y equals x. Now, I could also say, hey, when I see these points, if I flip those x's and y's, I know that this is 5, 1. I know that this is 6, 2. And I know that that's 7, 3. And there I go. I can create that inverse simply by taking the ordered pairs that are on this one-to-one function, flipping the inputs and outputs to get the points on this inverse function. Okay? So switching the x's and y's and solve for y is what I do algebraically, but numerically from a table, all I'm going to do is switch the x's and y's, and on a graph, all I'm going to do is switch the x's and y's, though on a graph I also know that f and f inverse reflect across y equals x. Okay? All right. That's fabulous. Switch the x's and y's, solve for y is what I do algebraically. Numerically, I just flip the inputs and outputs. Graphically, I flip the inputs and outputs. I'm switching x's and y's, I'm switching x's and y's, and algebraically, I'm switching x's and y's and solving for y. It's pretty dependable. Oh well, at least until we get to the next video. Okay, so to make an inverse of f of x, one, algebraically, what was it that we were supposed to do? Switch the x's and y's and solve for y. 2, numerically, or from a table. I want to switch the x's and y's. I mean, it may be that I'm switching a column of inputs with a column of outputs. That may be that Jeff should take that here. Okay. And 3, graphically, I want to switch the x's and y's on the ordered pairs. Okay, so maybe you could, I don't know, make an inverse or two for me. Here you go. Let's have a little inverse practice thing. So if I have x and f of x as -3, 2, 5, 7, and 4, -1, 0, 6. Here's a table for f of x. Will you please make an f inverse table for me? Pause the video, give that a try. Welcome back. So did you just, switch those columns? Switch the inputs and outputs? Because that's all I need to do. To go from f to f inverse, I'm just switching the ordered pairs. Okay? All right. So what about in this situation? What if I had f of x equals cube root of x minus 1 plus 2? Can you find f inverse of x for me? Give that a try. Come back when you're done. Okay, so we said in order to make an inverse algebraically, I want to switch the x's and y's. So I'm going to have x equals cube root y minus 1 plus 2. And then the second part was, not only do I want to switch the x's and y's, but then I want to solve for y. So I'm going to subtract 2 from both sides. What can get rid of cube root? Good, I need to cube both sides. Then cube root and cubing will undo each other. X minus 2 to the third. I'm almost there, but I still have to add 1 to both sides. And so I'm going to have x minus 2 to the third plus 1 equals y. Nice, nice. So, let's think about this. Instead of calling this y, I can now call this f inverse. This function is the inverse of that function. And if I think about graphing these, let's think about this. This is my cube root shifted left 1 and, shifted right 1 and up 2. So I'm shifted right and up 2. Boink. And that's 1, 2, and 2. Yeah, that's 0, 1 there, 1, 2, and 2, 3. So there's my cube root function. What about its inverse, this one? Well, let's think. We're going to take our x to the third function and shift it right 2 and up 1. So I'm going to be at 2, 1, and I'm going to go here, And I'm going to go here. That and that. Now, I know that these ordered pairs are in fact these ordered pairs where the x's and y's have switched. And there's my F inverse. And look, I mean, even on my crappy graph, it's pretty close to reflecting across the line y equals x. So we've got ways to understand making an inverse algebraically, graphically, and numerically. And that's fabulous. Yeah. I do want to talk about two things that are important. The first is parabolas. Yeah. You know, it turns out I'm not happy throwing away parabolas. We've spent a lot of time with parabolas in our algebra education, and to throw them all away because they don't pass the horizontal line test, yeah, it just makes me too sad. I know it may not make you too sad, but it makes me sad. And so we actually have a fix for this. Remember, in order to have an inverse, a function needs to be able to pass a horizontal line test. This one doesn't. And that's why parabolas, you know, they don't have an inverse unless, what if we, well, no, only looked at part of the parabola? What if we restricted the domain on the parabola so that we went to the vertex, from the vertex on, or from the vertex on? Either side, doesn't matter. And so if I want to do that, I need to do something like this. Now, I don't think you and I are going to be asking you to do this restriction. But I want you to know, when you see this restriction is there to allow you to make an inverse of this. Okay? Now, how do we do that? What are we talking about here? Well, graphically, we're talking about this. 0, 1, 1, 2. That's our original function. And so tell me about the inverse. Well, the inverse, because I'm switching the x's and y's from the ordered pair, is going to pass through 1, 0, and is going to pass through 2, 1. And so there's my inverse. Okay? I mean, works great. What happens, though, if I look at this part and have this point, negative 1, 2? Well, when I switch the x's and y's, now this point is going to become 2, negative 1. And look, I failed the vertical line test. So even though this wants to be the inverse function, yeah, sorry, it's not a function. And so, no. And that's why we need this. Okay? Let's try solving for, let's try actually making the inverse here algebraically. Okay, so I'm supposed to switch the x's and y's and solve for y. Now I take the square root of both sides. And what is it that I'm supposed to remember when I take the square root of both sides? There it is, the plus and minus. And guess what? This is exactly what's making my inverse not be a function. This leads to this, and think about what that looks like. Square root graph shifted right 1. That's the positive version. But now the negative version. It's the square root graph shifted right 1, and all the y's are multiplied by negative 1, and so I reflect over the x-axis. And because I had both this piece and this piece, I failed the vertical line test. And so this thing that I want to say is the inverse, yeah, no, it's not a function. But if I look at only part of this, then that is a function, and I can have an inverse. And that means this. X has to be greater than or equal to 0. So if I wanted x less than or equal to 0, this would be the minus thing. Okay? And when I say okay there, I don't mean you're really comfortable and you'd be very happy to write these restrictions. I will say you're actually much closer to it than you may feel. X minus 2 squared plus 1. And so where's the vertex here? Remember vertex form? 2, comma, 1 is my vertex. So on the inverse function, my vertex would be located at 1, 2. Yeah, no kidding. And if I want to restrict this, I want to say x is going to be greater than or equal to the x coordinate of the vertex. This one will have the restriction from 1 because of this plus 1 here. Okay. Yeah, again, I'm not going to really be asking you to do that. If this were honors pre-cal, sure, why not? I really am telling you all this so that if you see this, you don't freak out. The reason this is here is to give us permission to work with this in a way that will work, that isn't scary. What we do need to do, though, if we try and make the inverse of this function, is remember that when we take the square root of both sides, x equals y minus 2 squared plus 1, so I'm going to be subtracting 1. X minus 1 equals y minus 2 squared. I take the square root of both sides, and it's right here, right now, when I say plus or minus. Yeah, no. No plus or minus. I'm still going to add 2 to both sides. Square root of x minus 1 plus 2 equals y. This is my inverse function. Okay, this. If I put the plus minus down, that's going to fail the vertical line test. And so this inverse won't be a function, and I'll say I don't care about that. Okay? So, restricted domains. Be aware of it. The other thing I wanted to talk about was this word, verify. When you see this word has a very, very, very specific particular meaning in this context. When we're asked, are these two functions 1 half negative 1, 1, 0, 2, 1, 0, 1, negative 1, 1 half, and 2, no, 1, 2, there we go. Are these two functions inverses of each other? And we look and we say, yeah, they reflect across y equals x. Look at all the ordered pairs. They're just flipped x's and y's. We're really, we have this intuitive sense that these are, in fact, inverses of each other. And that's fine for casual work. But for proof, we need to be able to verify that this is true for all points, not just those 3 we had. I mean, there's an infinite number of points on each of those graphs. And so really to have, capital T truth, always true, for sure true, we need to verify. And verifying, you have to do it this one way. You have to do the composition of both f of f inverse and f inverse of f. And you need to get x both times. So let's verify that our two Bell-work functions are in fact inverses. Remember, we had f of x equals 3x plus 6. And then we had this other function, 1/3 x minus 2. And what I'm saying is, in order for me to verify that these two are inverses of each other, I need to do f of g of x, and I need to do g of f of x. And not only do these have to be the same, but they both have to be x. When you see the word verify, you can't just do one of these compositions. Get x and say, done. When you see the word verify, you have to do both compositions and show that both compositions get x. Okay? I did these in the bell work. I'm not sure you did. Did you? Try them again now. And then there's one last thing I want to see then. One last thing after that. Okay. Hey, welcome back. If I take g of x and plug it into all the x's of f of x, that's this in there. So I distribute, and I'm going to have x minus 6 plus 6 is x. Nice. But that's not sufficient. That doesn't prove, that doesn't verify that these two functions are inverses. I have to do this one as well, where I take this f of x and plug it in there. Don't forget that one. I distribute, and I get x plus 2 minus 2x. Ta-da! Because f of g and g of x and g of f are both equal to x, I know that f and g are inverses. Okay, well, there we go. I would say that you will be asked to do some exciting composition work. What do I mean by that? Well, here's f of x, 1/8 x minus 3, and here's g of x, which is x to the third. Now, are these inverses of each other? Yeah, no, they're not. So don't worry about that. But I can make the inverse. So what's f inverse going to be? Well, I switch the x's and y's. I get x equals 1/8 y minus 3. X plus 3 equals 1/8 y. And if I multiply both sides by 8, remember, it's the whole side. I get y equals 8x plus 3, or 8x plus 24. There's f inverse. Same thing with g. Switch the x's and y's. X equals y to the third, and solve for y. Y equals cube root of x. This means that g inverse is cube root of x. Okay? Now, how about this? How about I say, hey, so what's g inverse of f inverse of 2? So I would like you to say, oh, f inverse of 2? No problem. I just plug a 2 into f inverse. 2. 2 times 8 is 16. 16 plus 24 is 40. 40. So nearly 40. 16, 24, yeah, it's 40. And then I want g inverse of that number. And so g inverse of 40 means cube root of 40. I mean, I guess you could tidy this up because this is 8 times 5, so 2 cube root 5. But really, I just want to focus on how do I evaluate something like this. Because frankly, when a lot of students see this, they want to run away. They're very scared. And I appreciate that. I understand completely. I'm scared too sometimes. Except really, if I just don't get scared and instead say, oh, first I have to make the inverse functions. I have to plug a 2 into f and see what I get, or f inverse. So here's f inverse. I plugged in the 2, and I got 40. And then I still had g inverse on the outside. And G inverse of 40 means plug a 40 to G inverse. And so I had to find G inverse so I could plug the 40 in. Just like I had to find F inverse to plug the 2 in. Really, these are just composition problems, and you shouldn't be terribly, terribly scared of them. Here, though, is one for you. Let's see if I can put this in a place where it won't get lost. We know that F inverse turned out to be 8x plus 24, and G inverse turned out to be cube root of x. Okay? So let's do this one. In fact, you do this one. This is the one for you. No, we did that. I want this one. F inverse of G inverse of 8. Okay? Please evaluate that expression. Welcome back. Did you plug 8 into G inverse? Okay, so G inverse of 8 is the cube root of 8. And since 8 is 2 times 2 times 2, well, we know that's going to be just 2, because I need a group of 3 of the same, which I have, to get one out. So this G inverse of 8 can be replaced with 2. And now I want F inverse of 2. So I plug a 2 in here. 2 times 8 is 16, plus 24 is 40. So this expression is equal to 40. Good, nice, can do. Oh, by the way, instead of seeing this notation, you might see it as this notation. Yeah, like that. Yeah, I know this is the cool modern way from the 1800s, but really, I find this so much more, I understand what's going on. I have to find G inverse, I have to plug an 8 into it, and then when I'm all done, that value goes into F inverse. Here, yeah, I've seen students try and do this distributing thing, and it is not F inverse of 8, G inverse of 8. Yeah, no, that's just terrible, terrible, terrible. So it may be helpful to rewrite like that. Okay. I said that was the last thing, but I kind of really want to talk about this other thing for a second. And that is this. Remember how we said parabolas? And I said, no, don't worry. We'll do that. And so then we've got this F. This F inverse, then, would be square root of x. Or would it? Let's think about this. Okay? If I compose these, I get x. And we have known for a long time, if we do F inverse, in this case, we're taking this and shoving it in there, and we get x. And if we do F inverse of F, we're going to take this and plug it in there. And so look at that. And so we say, yes, look, behold, these are inverses of each other. Yeah, so it turns out that this isn't quite the whole story. If we graph this on our calculator, yeah, we get that. Remember, if you're composing these and they're inverses, yeah, we need that restriction there. And here is that. I know, right? Well, let's think about why this is happening. Okay, so this inside function is a square root. Can I plug a -1 in? No, I can't. And that's why I have to have this. So sure, square root and squaring undo each other, but I don't get y equals x. I only get y equals x for x values greater than or equal to 0. If I graph this on my calculator as written, I get this picture. And over here, what's happening? Well, what happens if I plug in -1 here? -1 times -1 is +1. Well, I get a 1 out. And if I plug in a +1, I also get a 1 out. If I plug in a -3, -3 times -3 is +9. Square root of 9 is 3. And what happens if I plug in a +3? 3 times 3 is 9. Square root of 9 is 3. And so look what's happening here. I plugged in a 1, I got 1. I plugged in a -1, I also got 1. I plugged in a 3, and I got 3. I plugged in a -3, and I got 3. And so look what we're getting. Yeah? That's a little freaky. It's a little freaky. Because for years we say squaring and square root undo each other. Squaring and square root undo each other. And it's not quite exactly always so. But now that we're talking about inverses, and we understand that the inverse only exists if the inverse passes its own vertical line test, well, in order for that to happen, only this, okay? Because that thing inside, that has a restricted domain, and so it shows up here. Okay, do you have to worry about this? No. But it will explain why you see some of this. And if you looked at the answers, say on Slater for our textbook, you're going to see some of this. Don't be scared. Okay? All right. I hope you have a wonderful day. I hope this was a helpful review. And tomorrow, I'd like to practice inverses a little more, but I'd also like to take a deep dive into inverses in word problems. Ooh. All right. See you there. Have a great day, everyone.